Hello dear friends, welcome back to MACSCollege. Now under matrices, in this session, we learn two important concepts. The first one is echelon form of a matrix and the second one is reduced row echelon form of the matrix. And we also learn two important methods. The first one is Gaussian elimination method and the second one is Gauss-Jordan elimination method. Before understanding the definition of row echelon form, I want you to understand what is a zero row and what is leading non-zero entry in a row. Zero row means a row with all zeros or a row containing all zeros. See, if you observe this, this is a zero row where all the elements in the row are zeros. This is a zero row. This is also a zero row. This is also a zero row. Here, this is a zero row and this is also a zero row. A row containing all zeros is called zero row. Otherwise, it is called non-zero row. So, this fellow is a non-zero row. Hope the idea of zero row is clear. Now, the second term which we need to understand is what is leading non-zero entry. Leading non-zero entry means the first non-zero entry in a row. Okay. So, if you consider the first matrix, in the first row, 2 is the leading non-zero entry. See, leading does not means highest, sir. It is the first non-zero entry in that row. Second row does not have a leading non-zero entry. But if you see third row, 3 is the leading non-zero entry. Leading means first non-zero entry. Please don't misunderstand as a highest non-zero entry. It is the first non-zero entry. Now, in this row, 3 is leading non-zero. This row and this row does not have any leading non-zero entries. 3 rows does not have any leading non-zero entry. In the fourth matrix, 8 is leading non-zero entry. In the second row, 1 is the leading non-zero entry. Third row does not have a leading non-zero entry. And the fourth row, 7 is the leading non-zero entry. So, please know these two concepts. One is what is zero row, a row containing all zeros. Leading non-zero entry means first non-zero entry in a row is called leading non-zero entry in a row. Okay. So, now we are ready to define what is row echelon form. See, these are not definitions, sir. I not defined here. Now, I am going to define what is row echelon form. So, important question which they can ask you is define echelon form of a matrix or define row echelon form of a matrix. So, what is the question? Define echelon form of a matrix. Some people also call it as row echelon form. Both are one and the same. A matrix is said to be in echelon form or row echelon form if the following two conditions are satisfied. So, whenever you want to say a matrix is in echelon form, these two conditions must be satisfied. What is the first condition? All zero rows, if any, must be at the bottom of the matrix. So, if you find any zero row, they must be at the bottom of the matrix. That is the first condition. Let us check. In the first matrix, first condition is satisfied. You see this is a zero row, but it is not at the bottom of the matrix. So, first condition failed. Now, here this is a zero row, this is a zero row. So, zero rows are at the bottom of the matrix. Therefore, first condition satisfied. If you see the third matrix, there is no zero row. If there is no zero row, no problem. If zero row is there, it should be at the bottom of the matrix. So, trivially, first condition is satisfied. If it is not there, don't worry. If it is there, it should be at the bottom of the matrix. Now, in this, all are zero rows. So, obviously, they are at the bottom. See, the idea here is after zero row, we should not get a non-zero row. See, if you see here, there is a zero row. Below that, you find a non-zero row. That is why it is failed. Am I clear? After zero row, we should not get a non-zero row. Please note. Now here, this is a 0 row. This is also a 0 row. But here below 0 row, you find a non-zero row. Therefore, first condition failed. So the first condition is clear. What is the first condition? All 0 rows, if any, must be at the bottom of the matrix. Now let us see the second condition. Each leading non-zero entry in any row is to the right side of leading non-zero entry in the preceding row. That is, if you find a leading non-zero entry in any row, it should be to the right side of leading non-zero entry in the previous ya to preceding row. Please note this idea very carefully. See, whenever you find leading non-zero entries, they must be in this format. Right side of that, right side of that, like that. Okay. So this is the order in which you should find this leading non-zero entries. See, how right, it does not matter, but they should be in this order. Suppose if you find like this, then it is failed. Suppose you find a leading non-zero entry and again next leading is to the left side, then also it is failed. So these two are failure cases. These are all correct cases. Success, success, success. Now let us check that. But please note, if the first condition is failed, don't worry about the second condition. First condition failed, it is not in echelon form. Because first condition is not satisfied, no need of verifying second condition. Here, first condition is satisfied. Now the second condition. Is second condition satisfied? You see leading non-zero entry. See, there is no other leading non-zero entry. If it is there, we have to check whether this is happening or not. So by default, it is satisfied. So it is in echelon. Now here, this is leading, and this is leading. And you see all the leadings are to the right side, right side, right side. So second condition is also satisfied. First condition trivially satisfied. Second condition also satisfied. Therefore, it is echelon. Now here the first condition is satisfied. Second condition, people say, sir, there are no leading non-zero entries. If they are present, then you worry about them. If they are not present, you don't have to show anything. Am I clear? So trivially it is satisfied. See, if at all they are present, they should be in this format. Please note that. So it is in echelon. Now what about this? Here first condition is failed, so not in echelon. Not in echelon. So what is the definition of row echelon form? A matrix is said to be in echelon form if the following two conditions are satisfied. What is the first one? All 0 rows, if any, must be at the bottom of the matrix. Second one, each leading non-zero entry in any row is to the right side of leading non-zero entry in the previous row. Let us take some more example quickly. Is it in echelon form or not? 0 row is not there, no problem. If it is there, it should be at the bottom. Second, now let us see the leading non-zero entries. Leading, leading, leading. Right side, right side. Second also satisfied, so echelon form. Now here there is no 0 row, but if you see leading fellows, first condition satisfied because no 0 rows, no problem. But second condition failed, you see. Here you see this leading non-zero entry should be to the right side of leading non-zero entry in the previous row, but it is to the left side of leading non-zero entry in the previous row. Therefore, this is failed, not in echelon form. Not in echelon form. Of course, in the examination, if you write one example, it is enough, sir. Now here there are no 0 rows, but you see leading, leading, leading. First condition is satisfied, but second condition failed because they are in the same column, failure. So second condition failed, not in echelon form. Now here, leading, leading, and 0 row is above non-zero row. So first condition itself failed. Don't worry about second condition, not in echelon. Okay, please note that. Now, which of the following is in row echelon form? So here 0 row is not there, no problem. Leading, leading, leading. Right side, right side. Second condition satisfied, echelon form. Now here 0 row is above non-zero row. First condition failed, not in echelon form. This is in echelon form. Here First condition satisfied, second condition. Trivial example. We call such examples as trivial example. And it is in echelon form. Now here, this is leading, this is leading, this is leading. Zero row not there, no problem, but the second condition failed. Second condition failed, not in echelon. Now let us talk about the next definition. Define reduced row echelon form. Some people also call it as reduced row echelon or canonical form also they can call it. But common or good name is reduced row echelon form. RREF, let us call it RREF. And here for this, there are 4 conditions. A matrix is said to be in reduced row echelon form if the following 4 conditions are satisfied. First of all, it should be in echelon form. Means what? First condition and second condition, which we already know, they must be satisfied. That is, all 0 rows, if any, must be at the bottom of the matrix. Second one, each leading non-zero entry in any row is to the right side of leading non-zero entry in the preceding row. So first of all, it should be in echelon form. Then third condition, the leading non-zero entries must be 1. See, if you see previous examples, the leading fellow can be 2. But if you want reduced row echelon form, what is additional condition? The leading non-zero entry must be 1. We call them as leading ones. We call them as leading ones. And the fourth condition is this leading one is the only non-zero entry in this column. That is, if it is a leading one in the column, remaining all fellows must be 0. It is the only non-zero element in its column. So if these 4 conditions are satisfied, then the matrix is said to be in reduced row echelon form. First one is all 0 rows must be at the bottom. Second one, leading non-zero entry in any row is to the right side of leading non-zero entry in the preceding row. Third one, leading entries must be 1. We call them as leading ones. And fourth one is leading one is the only non-zero in its column. That is, in that column, it is the only hero, remaining all zeros. Now let us check whether the 4 conditions are satisfied. We have to check 4 conditions. 0 row is at the bottom, satisfied. Second condition, leading right side. Second condition satisfied. But leading fellow is 2, third condition failed. Because you want leading fellows to be 1, that condition failed. So it is only in echelon form, but not in reduced row echelon form. Now next one. First condition, 0 row not there, no problem. If it is there, it should be at the bottom. Second one, leading, right side, right, satisfied. Third condition, all the leading fellows are 1s, third satisfied. Now fourth one, this is the leading one, in this column remaining all are 0. This is the leading one, in the column remaining all are 0. This is the leading one, in the column remaining all are 0. 4 conditions satisfied. So it is in echelon form as well as reduced row echelon form. Now next one, 0 row is at the bottom, satisfied. Leading, right side, satisfied. Leading element must be 1, satisfied. Fourth one, now you see this is leading one, in this column all are 0, satisfied. But here this is leading one, in this column 5 is failed. So fourth condition failed. So it is only in echelon form, but not in reduced row echelon form. Now here, first condition, 0 row at the bottom, satisfied. Second condition, leading, right side, satisfied. All the leading fellows are 1s, satisfied. Now fourth one, in this column all are 0. In this column all are 0, but in this column this is not 0. Fourth condition failed. So only in echelon form, but not in reduced row echelon form. Now before learning Gaussian elimination method and Gauss-Jordan elimination method, let us learn the following 3 important results. The first one is every matrix can be reduced to echelon form and reduced row echelon form using finite number of elementary row operations. That is, suppose you are having a matrix which is not in echelon form or not in reduced row echelon form, using row transformations or row operations, you can convert it to a matrix which is in echelon form. Again, this can be converted to reduced row echelon form using row operations. So, even if the matrix not in echelon form and not in reduced row echelon form, using row operations, how many? Finite row operations, finite number of row operations, it can be reduced to echelon form as well as reduced row echelon form. And two matrices A and B are said to be equivalent if one can be obtained from other by sequence of elementary row operations. So, original matrix is reduced to echelon form, then these two matrices are equivalent. See, please note, they are not equal matrices, they are equivalent matrices. Why we call them as equivalent matrices, sir? Because they are having same rank. And this is one of the important methods for finding rank. So, we also learn how to find rank here. So, how to find rank? First, they give you matrix, reduce it to echelon form. Suppose this is echelon form. From this, we can find rank. Number of non-zero rows in echelon form is called rank. Of course, I'll teach you that, but this is the best idea, my dear friend, best method to find rank. Okay. So, now let us understand the Gaussian elimination and Gauss-Jordan elimination method. But before that, we should understand this idea of rearranging rows. See, whenever you find any zero rows at the top of the matrix, directly pull them down. Okay. You can directly transfer the zero rows to the bottom of the matrix. See, if you see here zero row, na, directly what you do? Directly transfer zero row to the bottom of the matrix. So, remaining matrix changes like this. This is one step for rearranging rows. The second step is very important. See, here this is leading element and here it is leading element, leading non-zero element. And a row having more zeros before leading non-zero element should be below a row having less zeros before leading non-zero element. Because you know, if leading is here, next leading should be to the right, but here you see leading is to the left. So, you should rearrange the rows in such a way that this kind of arrangement is happening. That is, leading non-zero entry in any row is to the right side of leading non-zero entry in the previous row. So, whenever you find the bad arrangement of the rows, immediately rearrange them properly. Like this last row we are not changing, but this row goes to the top row and this row go to the bottom. See, while applying Gaussian elimination or Gauss-Jordan elimination, which I am going to teach you now, even in that, at every step, you have to check for this rearrangement of the rows. Whenever there is a bad arrangement of the rows, we should rearrange them properly. If you find zero row somewhere at the top, you should immediately pull that down. And secondly, arrange the rows in such a way that a row having more zeros before leading is below a row having less zeros before leading non-zero element. So, this is what you mean by rearrangement of the rows. Please note that this is very, very important. So, you have to do these steps every time whenever it is required. Okay. Now, let us move on to the actual method called Gaussian elimination method and Gauss-Jordan elimination method. Of course, we can call them as combinedly as elimination methods. Okay. And as I told you, rearrange rows at each step if required. Whenever required, you have to rearrange the rows. So, if you find zero row at the top, blindly pull that down. Secondly, arrange the rows in such a way that a row having more zeros before leading is below a row having less zeros before leading. then you can continue your procedure. Okay. So the first method is apply forward elimination to get echelon form. I'm going to teach you this forward elimination, and this is what we call it as Gaussian elimination method. This is what we call it as Gaussian elimination, or some people also call it as Gauss forward elimination. It is also called as Gauss forward elimination. The name, sir, nothing more than that. Gauss forward elimination or simply Gaussian elimination. Now, after getting echelon form, what we do is we do backward elimination to get reduced row echelon form. We do backward elimination to get reduced row echelon form, and the second step is called Gauss backward elimination method. What is it called? Gauss backward elimination method. And there is one more method which I told you, like Gauss-Jordan elimination. If you combine these two methods, that is what we call it as Gauss-Jordan elimination method. The combination of both methods is Gauss-Jordan elimination. Only forward elimination is called Gauss forward elimination or Gaussian elimination. Only backward is called Gauss backward elimination, but forward plus backward is what is called as Gauss-Jordan elimination method. So let me start with forward elimination. Okay, see, it is a systematic method. For any problem, you can apply forward elimination in a very systematic manner to get the result. See, the idea here is we want to reduce matrix to echelon form. Reduce matrix to echelon form. And what is echelon form, sir? 0 row must be at the bottom. 0 row must be at the bottom. So whenever you find 0 rows, now directly pull them down. So first condition can be easily obtained. Second one is the leading non-zero entry in any row is to the right side of leading non-zero entry in the preceding row. So we need to get this kind of arrangement. Okay. Suppose by rearranging rows, if you can get it, get it. Otherwise, by doing row operations, we should get it. Okay. Now let us see what is this forward elimination. Now if you see, this is leading element, this is leading element, and this is leading element. And if you see, all the leading elements are in the same column. But what you want, after first leading, next leading should be to the right side. So if you want next leading to the right side means, what should happen to these two elements? If you want next leading to the right side means these two fellows should be 0. And that is what you mean by forward elimination. You are making them zeros by row operations. Forward elimination. So how to make this equal to 0 using this? How to make this equal to 0 using this? See, you have to fix this, and using this you have to make these two fellows zeros. Systematic method. Second row is second row minus first row. So 1 minus 1, it becomes 0. Similarly, third row is third row minus 2 minus 2, not 2 times of row 1. So this is the new matrix. So here first row remains as it is. Here first row remains as it is. Now here 1 minus 1, 0, 2 minus 1, 1, 3 minus 1, 2, 6 minus 4, 2. This row operation I applied. Every element 1 minus 1, 2 minus 1, 3 minus 1, 6 minus 1. Again now R3 is R3 minus 2R1. So 2 minus 2, 0. 3 minus 2 into 1, that is 3 minus 2. 3 minus 2 is 1. 0 minus 2 into 1, that is 0 minus 2 minus 2. 14 minus 4 into 2, that is 14 minus 8, that is 6. And if you observe, this is leading, next leading is to the right side of it. So up to here the condition is satisfied. Now the next leading should be to the right side means this fellow should become 0. So you have to apply row operations in such a way that this is 0. So how to make it, sir? R3 is R3 minus R2. So what happens? This is first row as it is, second row as it is, and the third row 0 minus 0 0, 1 minus 1 0, minus 2 minus 2, that is minus 4, 6 minus 2, that is 4. Is the idea clear? So this is your echelon form. See, here it is leading, here it is leading, here it is leading, right side, and you got echelon form. So this is called echelon form of this matrix. Let us call it as a echelon form of it. And once you got the echelon form, you can find rank. Rank is how many non-zero rows are there in this matrix. In this matrix, how many non-zero rows are there? All are non-zero rows, so 3 non-zero rows, that is rank. So echelon form can give you rank directly, and this is the easiest way to find rank of the matrix. Easiest way to find rank of the matrix. Okay, so please note that. What is rank? It is actually method to find rank, sir. Of course, some people also give it as definition, but that is not a good idea. Method to find rank. What we need to do? Reduce matrix to echelon form using Gaussian elimination. That is Gauss forward elimination or simply Gaussian elimination. Then number of non-zero rows in echelon form of a matrix is called rank of it. So we'll have a separate session where we take problems to find rank using Gaussian elimination method. Am I clear? That is using echelon form. You can call it as using echelon form. You can call it or using Gaussian elimination. Separate session we have where we solve the problem. Is that clear? Now let us see Gauss backward elimination method. To apply this method, first of all, the matrix must be in echelon form. So we apply Gauss backward elimination method to get reduced row echelon form of the matrix. So reduced row echelon form means first of all matrix must be in echelon form. That is first and second condition must be satisfied. Third condition, that is leading non-zero element must be 1. Fourth condition is leading 1 is the only non-zero element in its column. Is the only non-zero element in its column. That is, if it is leading 1, in that column remaining all elements must be 0. So we should apply row operations such that these two conditions are satisfied, and that is what we call it as backward elimination method. Okay, please note, first of all matrix must be in echelon form to apply backward elimination. So here we start with the last row having or last non-zero row. We start with last non-zero row, and here what is the condition? The leading fellows must be 1. But if you see this element is minus 4, so you make it 1 using row operation. How I can make it 1, sir? Row 3 is row 3 by minus 4. So what happens? Because we are only applying operation for third row, first and second row remains the same, but the third row 0 by minus 4, 0 by minus 4, minus 4 by minus 4, 4 by minus 4. Now you see this leading fellow is 1, and what is the fourth condition? Leading 1 is the only non-zero element in its column. That is, these two fellows must be 0. So what we do is, using this element, we try to make these two elements 0. So we are making 0 using backward elimination. So what is the row operation we are going to use, sir? R2 is R2 minus 2 times R3, and R1 is R1 minus R3. See, this is fixed, Using this, you are making these two fellows 0. That is, R1 is R1 minus R3, R2 is R2 minus 2R3. So with this, we are going to get new matrix. What is it? Last row remains same. Now, what about the previous row? This 0 minus 0, because R2 is R2 minus 2R1. 0 minus 2 times 0, 0 only. 1 minus 2 times 0, that is 1 only. 2 minus 2, which is 0. Then 2 minus of minus 2. So here 2 plus 2 you get. See, 2 minus 2 into minus 1, which is 2 plus 2, which is 4. So you get 4 here. Then next one, R1 is R1 minus R3. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. Then 4 minus of minus 1. 4 minus of minus 1, which is 4 plus 1, yani 5. And you see this is 1, and in this column remaining all elements are 0. So for this leading, this two conditions are satisfied. Now we move on to the next non-zero row. And first make the leading element 1. Luckily, it is already 1. If it is not 1, you have to make this 1. Once it is 1, the element above that must be made 0, because it is the only non-zero element in its column. Already the element below it is already 0, so we have to make this element 0 using row operation. How to make it 0, sir? Simply using this, you have to make it 0. How? R1 is R1 minus R2. So what happens? The third row, 0, 0, 1 minus 1. Second row, 0, 1, 0, 4. And this one, 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 0 is 0, 5 minus 4 is 1. And this is leading 1. In this column, all are zeros except this. This is leading 1, except this, remaining all 0. Now you have to make this leading 1. It is already 1, no problem. If it is not 1, you have to make it 1 by using row operation. Now this is your reduced row echelon form. This is your reduced row echelon form. Of course, there are some special problems, like, for solving system of linear equations, for finding inverse of the matrix, we require this reduced row echelon form. Even under eigenvalues, eigenvectors also, this may be required, especially for eigenvectors. And please note, Gauss-Jordan method or Gauss-Jordan elimination means forward elimination plus backward elimination. That is, first you have to do forward elimination. After that, see, after you get echelon form, that echelon form you have to reduce it to reduced row echelon form. So combination of these two is Gauss-Jordan elimination. Please note.